Hi, I'm Sazan Mahbub. I'm from Carnegie Mellon University, Computer Science School. We're actually working on a problem of zero-shot clinical prediction in heterogeneous environments. So we actually propose a new method called RAG-IM that adapts any pre-trained language models to any specific new scenarios. So the motivation is that clinical predictive models need to adapt to various environments. So various settings like various hospitals and different populations have different kind of complexities. And if we can really represent them properly, then it will increase the accuracy and also the utility of the problem systems. However, the main challenges we face are that like there are much heterogeneity. We have to capture them, and also we have to maintain interpretability because we want to apply some deep models due to lack of interpretability. It is very hard to apply them, and also in clinical domains or many of the real-world application, there is very limited data or maybe unavailable. The training data is not available at all. So our proposed method is retrieval augmented generation of interpretable models. So this approach is actually a meta-learning approach to generate some interpretable machine learning model itself using the prior of existing pre-trained language models. And we actually generate task-specific and interpretable models for every single given task description. How we do is, and we retrieve and integrate existing other models properly from the related tasks. So going to the method, so this is the overall pipeline of our method. So since it's a RAG approach, we start with a vector database. In our vector database, we actually customize this. It has vector embeddings of the task description of bunch of tasks. So in our case, in our experiment, we have more than 4,000 different tasks. So we have 4,000 different task description of each of them, and also their features and labels. So what we can do, we can actually take the task descriptions and create language model embeddings of those. And from their features and labels, we can actually train with some optimization algorithm some very simple linear models. And in our vector database, we store all of them, and then we have this retrieval module. So if the task description of a new task comes in using a language model representation, we retrieve some of the relevant ones from vector database, and we do a weighted summation of them that gives us a new task-specific models. So as you can see, for this pipeline, for a new task, we don't really need any training data. So this is actually totally like hyper network. Okay, so the model generator itself is basically a three-layer, in our case, just a three-layer transformer. It can be customized as well. In this case, the value projection or the value, in the self-foundation of the transformer, the value is actually the linear models we retrieve from our vector database. The key projections are actually the language model embeddings of the test description, and query, as expected, is actually the language model representation of the new task description. So based on the query, we actually amalgamate the information from this retrieved elements and generate a new one. If you look at the how this is propagated, this is actually a linear combination of these ones. We actually explicitly maintain that for interpretability. Going to the dataset and analysis, we evaluated our methods on mainly 4 dataset, which is a very widely used medical dataset, where there are more than 7,487 different tasks. So every single task is a clinical procedure. So it's some binary classification tasks. So after pre-processing, we have this many tasks, and here this part is interesting. So if you look at this graph, this is actually showing this orange distribution here is actually showing the number of samples in every single task, and it is a very, very long tail distribution. So if you look at this region, for most of the tasks in actual real clinical worlds, we don't have that many training samples. So what we want to do, we want to transfer the learning we have here to this regime. So we call this the few-shot regime, where we have 2 to 4 samples probably for training. That is not good enough for training model. And for this regime, this is totally zero shot. That is, we don't have any training samples. So the only way to do it is actually through meta learning. That's why our approach is actually really applicable here. And we compared our framework with the baseline. The baseline is basic logistic regression. So here we can see that in high data regime, our model performs decently, but if we go to low data regime, while the baseline's performance significantly drops, at this point it's totally random, and for zero shot, the performance is actually not available at all because we cannot train in model. But our model's performance actually is consistent across all the regimes. So conclusion, our method actually tries to enhance interpretability and adaptability while maintaining, for low data regime and heterogeneous environments, feature work will enhance on top of this with learnable retriever and better language models. Yeah.